So what you're going to do in this exercise is now we're finally going to work with real spatial fire data. So this is the time series that you're going to be working with for that same landscape. So here's the actual fires. I'm not sure if these, do you remember, Leonardo, if these match the area burned? No, they probably don't. They're probably not the same as what you used in the last exercise. Doesn't really matter. But now you're going to come in with this time series. Well, certainly it's much shorter. The other time series was 30 years. This one's only 10. But you're going to do work to replicate this pattern spatially and temporally in your simulations. And so to do that, we're going to be, just going back to the slides here. So this is the idea where we want to create a pattern on our landscape that in our case reproduces something we've seen historically. And so if we do that, we're going to create what are called spatial multipliers. And the basic idea with these multipliers is you're now providing a raster instead of providing just a time series of multipliers, which were multipliers that were specified for all cells of a particular characterization, be it strata or state class or whatever. Now you're down and you're controlling, if you want, what multiplier gets applied for each transition, for each cell in each time step. So it can be that specific, and we call these spatial multipliers. So you generally provide a time series of these, and then, if you set up the multipliers to be 0, 1 values, then what it will do is it'll cause no transitions to occur in all the cells with zeros, and force the transitions to occur with certainty, probability of 1, in those cells that you give it a 1. And you could have multipliers of other values. They don't have to be zeros or ones, but this is a common way to do it. And so that allows you to force the transitions to occur, say for fire in this example, only on those cells that have the multipliers that are non-zero. And again, we can, when you set up these spatial multipliers, why do I have that in there? You can't do distributions with multipliers, can you, Leonardo?
No, but I think there what you have is you've got a fire size distribution. At least that's what that's labeled.
Right. So the idea with this slide, I did this a couple of days ago and I forgot why I put it in, is that that's one way you can create pattern on the landscape. And the other is what we showed yesterday in the exercise, where you can characterize the distribution of fire sizes and have STSIM sample from that and put them down randomly on your landscape. But these are the two alternative ways of doing patterns, and in this exercise we're going to look at this second way, which has more control, the one we're using spatial multipliers. That's all I had to introduce the exercise. Any questions before we start? No?
I have a comment, Colin.
Yeah.
This is one of the most important features in STSIM for our work. If you have grazing allotments, livestock grazing allotments, and you have to control, you have seasonal use of livestock, like summer, winter pastures or things like that, or if you have any form of management that needs to be spatially controlled, this is how you do it.
Yeah, common thing we do with it, for example, is we were talking about urbanization yesterday and trying to get the cellular automata model to grow it out. You can use multipliers to represent, say, zoning regulations. So you can put multipliers of 0 in areas that are protected from development, and put 1s in those areas that are zoned so that the urban growth happens only in those areas where it's allowed. Or you can have higher multipliers along roads, or you can shape the spatial pattern of transitions by constraining it and then allowing it with other features to grow in other ways, but use the multipliers to provide some base constraints on where the transitions occur. Is another example of how it gets used a lot. So as Louis said, it's a lever that gets used a lot. It's quite powerful. But the downside of the power, right, is that to use it, you have to come up with rasters rather than single values for your multipliers. And sometimes those are okay if they don't, like a zoning map doesn't vary over time. But sometimes you've got things, if you're trying to put a whole time series in there, you can have 100 of these maps if you're trying to control, say, exactly where fire occurs in every time step. So they can blow up into larger sets of inputs. You'll see it as you go through the exercise a bit of that. Yes, Anna, did you have something you want to say?
Just on that, Colin, with the thinking about fires, so could you have a time series of these maps that are used for their transition multipliers? And so if the fire occurred in a particular spatial location in year 1, in year 10 a fire wouldn't occur in that location that occurred in year 1, for example, and so on. So it depends, the next multiplier in the next year depends on the spatial location in the previous year.
Yeah, there's probably a couple ways you could get that dynamic. I usually defer to Leonardo on these ones if you want to chime in. I mean, I could think of one way to do it with time since transition, probably combined with multipliers, but Leo, did you want to comment?
Yeah, I think there's a feature that Colin mentioned. I don't know if you're not covering time since transition in the course, right? So, but you'll mention it towards the end, I imagine, that lets you set sort of contingency on what's happened, the history of the cell for future probabilities. And then the other approach would be to use this more spatial approach where you're turning cells on and off. So presumably if you've turned something on 1 year, you can turn it off for the rest of the simulation if you want, as another option.
I mean, the most sophisticated way to do this, again, like the more sophisticated, the more control you have, usually the more work it is. And so there are projects, actually I think we're going to show one at the end of today, it's one of Louis' projects, where you can pause the simulation at every iteration of time step, so you can put in breakpoints in your simulation. So you can run the simulation forward a year, pause, hand the landscape off to an R script in Louis' case. It can analyze it, decide where it wants to put transitions in the next time step, right? Based on whatever you want. Hand back to STSIM a spatial multiplier for the next time step. So create the multiplier on the fly, start STSIM up again. It takes that multiplier and modifies its behavior. So people are doing that now. That's probably the most sophisticated way to, and once you can do that, you can do, again, it's one of these levers that allows you to do virtually anything, but it comes with a cost of having to set up all this code, and it slows your simulations down enormously, by passing stuff back and forth between two programs. But like a lot of these things, they're eventually ultimately doable. So in this exercise, I think it was fairly straightforward. We were just looking at setting up different ways of controlling the pattern of fire spatially. So to recap again, we used the spatial multipliers feature, which we can get at from here, to force the fires to occur in certain cells in each year using a TIFF file that told us where the fires were. And then the idea was these are multipliers, so really we were shifting the probabilities by the amount in the multiplier files, these spatial files. So they're 0, 1 files, so we had to go over and set the probabilities, the base probabilities, to be 1 for fire, at least in the early period, in the 2003 period. We set the probabilities to be 1 here, these 3 values here, so that, and this is why I told you yesterday, we have this convention of setting the probabilities to 1 for transitions that we don't plan to set the probabilities directly in this table, so that we can go and set those probabilities elsewhere. So in this example, we used the spatial multipliers and gave them the probability we wanted for fire, which was 1 in some cells and 0 in others. We could also have used targets you've already seen, but if we can also use transition multipliers, and this is very common. We could have made the fire transition probabilities vary using transition multipliers, the aspatial ones, where again, if these probabilities are 1 here, the values we put in for the transition multipliers, if they weren't, being confounded with spatial multipliers, would also represent the probabilities. So that's quite a common convention to set these to 1. That was why in 2014 we brought in this made up TIFF file that had 1 values for every cell in the study area, and that way we were sort of setting the multiplier value to 1, which means it's having no effect going forward. It's taking whatever probabilities you calculate elsewhere in the model, multiplying by 1 in every cell. So it's a way to eliminate the effect of the multipliers from that year forward. So it's a little bit of a trick that you have to do when you're working with these kind of things. And so we ran those 2 simulations, one with the future fire being non-spatial and then spatial. So if we look over at the resulting maps for fire over the whole period, both historical and future, you should have seen something like this. The top scenario is the spatial one into the future. The bottom one is the non-spatial. Both are replicating the historical pattern of fire over the historical period using the multipliers. And then once we hit the future, we see that we've lost the menus, but it's the bottom one that's non-spatial. This is the kind of pattern we had in the last exercise where there's no aggregation of the fires, and here now we're getting fires again produced according to, in this case, the temporal multipliers and the size distribution we put in. So one question is, could we have used spatial multipliers out into the future? So does anybody have any thoughts, ideas on how we might have used spatial multipliers into the future as well? How could we have done that? Any ideas? I'm trying to see if I can see people's faces or not. Where did everybody go? There they are. Anybody?
Do you mean over and above just copying and pasting rasters and relabeling them with future years?
Yeah, so to get some variability, yeah. So, I mean, rather than how could we in STSIM reproduce, say, the variability we saw in fire in the past out into the future using spatial multipliers?
You just use the distribution from the historical data, like the patch size distributions.
Yeah, that's probably something like that I would do. I might analyze the historical time series of fire, and somehow you have to generate future patterns of fire. Actually, I can't really think of a way to do it, come to think of it, because unless Leonardo has an idea, but the challenge if you use spatial multipliers for future fire is you can't figure out a priori what's going to burn where, which is what you're required to do if you use spatial multipliers. You have to tell it, in this time step, burn this cell, and you can't know ahead of time what the vegetation is going to be on your landscape in your future years, and so you can't sort of set those up ahead of time, right? But having said that, the way you could do it is using that pause feature that I talked about at the last exercise. where you could run your model forward one time step, stop, take your projection of your landscape and your age, so your state and age, those are two rasters that you have at a particular time step in the future, pass them to an external model, like a fire model that you might already have, run that fire model, say a fire behavior model, for that 1 year, have it predict where the fires would occur based on what it sees for the landscape. It can include stochasticity, it can include whatever you like in that fire behavior model. It predicts where the fires are. At the end of running that fire model, you have a script that generates the spatial multiplier file for the next time step, or for that time step, hands it back to STSIM. STSIM applies it and burns the cells for that Monte Carlo and that time step, exactly as the fire behavior model would have done with that same information. And I think, Leonardo, aren't you doing that right now in one of your projects?
Yeah, we did that. We just published a couple of papers, one in Scientific Reports and one in Ecosphere, where we used the Farsight fire growth model. We're projecting buffalo grass invasion in the Sonoran Desert. And so this is an area where there's no historic fire data because there wasn't fires until recently. So we couldn't use the kind of approach that Colin showed in this exercise where you have a historic fire distribution. So instead we projected the invasion of buffalo grass and then used Farsight every time step. We created random fire starts based on the historic distribution of lightning strikes in the area, and then occasionally those strikes would hit buffalo grass, and then Farsight would model the fire perimeter for that fire, and then we'd bring that back into SDSIM. I can send that paper around as well, or those papers around if folks are interested.
Yeah, I don't know what you do in Australia, for example, you must have your own library and plethora of fire models, I would imagine, given how much fire you have to deal with. So I don't know if that's a possibility for you. I mean, that's pretty advanced and sophisticated, right? It can really slow things down computationally, as you can imagine. The kind of modeling that we show here, where you're characterizing the fire just in terms of frequency and size distribution, is a very simple yet efficient way to do it for a lot of our questions. Kind of what we
Yeah, one challenge we had with Farsight is that, well, first it runs on Windows, so we couldn't run it on HPC, and then the second is that you can't have two instances of it running at the same time. So we couldn't have, realizations running in parallel for that. So that really limited the number of Monte Carlo realizations we could do.
But I think what we're finding is we have a number of clients who are asking for this from us. I think it's a new frontier for us because it hasn't been really possible to run fire behavior models over large landscapes like we're doing here with Monte Carlos and all that. It still is very difficult, but with computational advances and so on and so forth, it's becoming more tractable and people are asking for it quite a bit. Just before, I'm going to turn to Leonardo to go up to answer the bonus question for you, because I realized 5 minutes before I said I'd take up the question that I hadn't actually prepared it myself, so I got him to do it. He does it several times faster than me. But I just wanted to point out the other thing that we were kind of covering in this exercise was the concept of sub-scenarios. Kind of slipped that in, just became an easy way for us to set up this exercise. It's it's a feature we try not to cover in the intro course, but it's actually a feature that everyone who uses SDSIM operationally takes advantage of. So I just wanted to show you a little bit further. I'll give you an example. This is the Hawaii model again, and in here we have, let me just close it up. This is pretty typical of how we set up one of these projects. We have a folder called full scenarios and a folder called sub scenarios often. And so these, in this particular library, it's the one that went with the publication, so there's only 3 scenarios I ran in here. When we had an operational version, there could probably be dozens of these. But the idea is that we create these sub-scenarios, and this is kind of our convention. We create a subfolder for each of the possible inputs. So under run control, we might have, you know, a half dozen different ways that we control run control. And let's just take a look at, say, targets. You know, each one of these scenarios has a different set of targets, but if I open it, it only has values for targets, right? So that's one set of assumptions for targets. You know, there's another one, you know, with fire only, with whatever they are. So we create a libraries of these building blocks, and we tend to do this where we sub-scenarios contain only one data feed at a time. And then what we do is we kind of combine them all into a master file with a whole bunch of dependencies where we pull, you know, one scenario for the transition size, one for state attributes, one for whatever. So we build them up like that. And it can even get more complicated if you really look at one of these ultimate scenarios in a quite complicated project. It's dependent on this scenario here, which is some combination of other building blocks, which in turn, you know, is dependent on all, you know, all these, which in turn, you know, and one of them is dependent on these, and one of them is, like, you can nest them and build hierarchies. So there's a very, very powerful suite of tools in SynchroSim to allow you to mix and match and to make it really easy to do sensitivity analysis and to mix and match your inputs in different combinations. Again, it's you figure it out pretty quick as you start working with this stuff for real, but I just wanted to point that out. Before I turn the screen over to Leonardo for the bonus, anybody have any questions or comments at this stage?
Quick observation, people probably notice every time we add a menu, the simulation gets slower and slower. Noticeably on your processors, you probably see it going slower. So it gives you an idea of, you know, more things take more time.
Yeah. The magic number of 6 Monte Carlo simulations or realizations that we've been doing in this course is a favorite of mine because I have a computer with 8 cores and I like to do 6. So whenever I'm testing models, I'll run them sometimes with 1, but often I just do 6 because it's just as fast with the multiprocessing. Get some idea of the variability, and then when you want to do production runs, you bump it up to 40 or 100 right at the end, but you play around with a low number just to get going. It's another common thing we do to deal with processing time. Leo, can I hand the control over to you? How do I?
Yeah, sure. I'll share my screen.
You can take it over from there. You're an organizer.
Okay. Can everybody see my screen with the kind of the bonus question here?
Yeah.
Yeah. So the question was if we could add timber harvest to the model for the prospective period, which I think begins in 2014. We assume the same harvest level and pattern as the bonus question at the end of exercise 3, which was that aggregated harvest kind of moving across blocks in space. And then it also asked us to say, create a spatial pattern where clear cuts 10% of them can be between 500 acres and 5,000 acres. So I'm kind of assuming that 90% are going to be 500 acres or smaller. So a couple of different inputs required for that. So the first thing I did is I actually went to the exercise 3 solution and I grabbed this aggregated harvest pattern from the transition targets, but I had to make a couple of edits. I don't know if people notice in this exercise, the blocks are don't have the blocks lettering, right? So I had to do a little bit of editing of the file before bringing it in because it wouldn't let me bring it in. You know, there's that issue that people had of bringing files in that don't have quite the same matching definitions. But anyways, here's what I brought in, and just because I was in a bit of a rush, I just put in 2003, the model starts, and saying no harvest at all in 2003. And then starting in 2014, I turn on the harvest for block A and off for everything else. And then this pattern of every 4 years, turning it off in the one that it was on previously and on for the next one. So that was one input. And then the second input was to the transition spatial size distribution. We had to add 2 rows for harvests. Starting in 2014, I want 90% of my harvest blocks to be 500 acres or less, and 10% to be somewhere between 500 acres and 5,000 acres in size. And so I ran that simulation, and so we can look first of all at a chart of harvest by block. And so here we have, starting in 2014, 3,000 acres in harvest block A for a few years, then trying to meet those 3,000 acres in harvest block B, not quite managing it, and so on and so forth across the different harvest blocks. And then as far as the spatial pattern is concerned, so we can look at a map of harvest. And I'll just move this window out of the way. And so again, this is a map of harvest starting in 2014. And you can see now we've got the spatial pattern with much larger harvest blocks. And also the harvest blocks are moving around the landscape a bit where they're being concentrated over time according to that pattern every 4 years. Although, I mean, I don't have a map of the actual harvest blocks to put alongside that, but based on the chart, I would expect that you'd see in the first 4 years harvest only happening in the areas that are designated as harvest block A. And I think that that was it. Colin, did I miss anything?
No, that's it. I think that's good. Thanks.
Yeah.